This is a 50mm f1.8 lens. Photographers describe lenses with those two numbers, the focal length and the f-stop. But that can be really confusing because a 50mm f1.8 lens produces completely different pictures depending on the camera that you put it on, at least depending on the sensor size in the camera. I have 3 different cameras here. This is a full frame 35mm camera. The sensor size is based on old film cameras, a format that dates back to about 100 years ago. This is an APS-C camera. The sensor size is quite a bit smaller. And this is a micro four thirds camera, which has a smaller sensor still. The good news is, in many situations, you can get exactly the same results with any of these 3 cameras. Sensor size doesn't usually need to hold you back. However, if you're buying new lenses, if you're thinking about switching from one size sensor to another, or if you're just considering how you're going to upgrade your camera gear, you'll need to understand how this one lens performs on each of these 3 cameras. Fortunately, there's a very easy conversion that you can do called crop factor. With crop factor, just like converting from miles per hour to kilometers per hour, you just do simple multiplication. Each of these different cameras has a crop factor that we've assigned to it. Full frame cameras have a crop factor of 1, which of course you multiply anything by 1 and it stays the same, right? APS-C cameras like this have a crop factor of usually 1.5. Canon cameras like this have a crop factor of 1.6. Micro four thirds cameras have a crop factor of 2. Something like your smartphone might have a crop factor of 7 or 8. Allow me to demonstrate this with my assistant here, my dad. You sit there and I will take pictures of you. First, I'll put this on the full frame camera. Now the APS-C camera. And now the micro four thirds camera. As you can see, the 3 cameras produced very different images with the same lens. All of the images have the same brightness, because sensor size does not affect the brightness or the exposure of your image. However, it changes just about every other property of it. With the smaller sensors, it was like I zoomed in, like I actually got closer, even though I didn't. That's because they're capturing just the center part of the image that the full frame camera saw. And if you were to overlay these 3 images, you would see that they line up exactly. In fact, those images are as if we cropped them from the middle of the full frame camera. Photographers don't allow the sensor size to dictate the composition of their pictures, and that's why people with cameras that have small sensors aren't taking only telephoto pictures. No, we have a vision and we use the right lens and the right focal length to accomplish that vision. If you have a smaller sensor, you would use a lens that has a shorter focal length to get the same angle of view. So this is a 50mm lens, and if I wanted to get that same angle of view on an APS-C camera, I would divide that 50mm by the crop factor, which on this camera is 1.6. On most APS-C cameras, it's 1.5.
50 divided by 1.6 equals 31.25.
On this micro four thirds camera, the crop factor is 2. Therefore, I would need a 25mm lens. So let me put lenses on these cameras that accommodate the crop factor and give me the same angle of view, and we'll see what I get. Okay, I have an 18-35 lens here. That'll work better on this APS-C camera. Let me dial in that focal length and take another picture. This micro four thirds camera has a crop factor of 2, so I need a 25mm lens, and I just happen to have a 25mm lens. That's a good start. My assistant here is now the same size in each of the pictures, but there's still something different. If you look at the backgrounds, they're very different. The picture from the APS-C camera has less background blur than the picture from the full frame camera. The picture from the micro four thirds camera with its smaller sensor has even less background blur. I used the same settings on all 3, but adjusted the focal length to match the composition. It was f4. f4 on this camera produces less background blur than it does on this camera, which is less background blur than it does on this camera. What if you want to add more background blur? That's a common compositional technique for photographers. Background blur is used to separate the foreground subject from the background subject, and it can help tell a story. Good news, you can get all the background blur you want out of small sensor cameras. Just use the crop factor and apply it to the f-stop. While this camera was 50 millimeters and f4, I would divide 4 by 1.6, back to the calculator, and that gives me f2.5. Take another picture. And with the crop factor of 2, I divide 4 by 2, which gives me an f-stop of 2. Let's take another picture. Good, so we can all be friends. Big sensors, little sensors, you can get the same result. You just have to know how to do this one simple conversion. Divide your focal length by the crop factor of your camera, and then divide the aperture, the f-stop, by the focal length of your camera, and you will get identical pictures. Now, if you've studied chapter 4 of Stunning Digital Photography, you know that f-stops are part of the way that the camera exposes the picture, and this exposure determines the brightness of the image. So when I switch this camera from f4 to f2.5 and this camera from f4 to f2, that would change the exposure of the image and should have made the pictures brighter. To accommodate for that and to keep the brightness level the same, I adjusted the ISO down. There's an easy formula that you can use to figure out the ISO too. Divide the ISO you would use on your full frame camera by the crop factor squared. So we started out with ISO 400 here. I divide 400 by the crop factor 1.6 squared, and that gives me an ISO of about 160. For this camera, divide 400 by 2 squared. 2 squared is 4, so I end up with an ISO of 100. Now we have complete equivalence. Focal length divided by the crop factor, aperture divided by the crop factor, and then ISO divided by the crop factor squared. Actually not that hard. This overcomes all the limitations you've heard about with small sensor cameras. Not only do you get the same amount of background blur, but you'll get the same amount of noise, especially in low light, because you're using a lower ISO. Now, the f-stop and the focal length, those are pretty exact conversions. The ISO, when you divide the ISO by the crop factor squared, it's not an exact conversion because these cameras have different sensors, and there is a little bit of difference in how different sensors perform in low light. However, if the cameras are about the same generation and the sensors are about the same generation, the results should be pretty similar. It's at least enough to get you a really good estimate of the amount of noise that you can see here. So in this case, yes, this small sensor was able to produce images that have about the same noise as this full frame camera. But wait, there are limitations to this. This monstrous lens is a 105mm f1.4, and it's huge. And it's designed for full frame cameras like this Nikon D850. And the effects of it are amazing. It produces fantastic amounts of background blur. As a portrait lens, it creates a look that's kind of unbeatable. I would love it if I could get this exact same look for APS-C cameras or micro 4/3 cameras. But here's the thing, the numbers don't really work out. Do the crop factor math and you figure out that for an APS-C camera, you would need a 70mm f0.9 lens, and for a micro 4/3 camera, you would need a 53mm f0.7 lens. And those lenses don't exist. You can't go buy those lenses. And that's where crop factor starts to break down. You want a particular effect, but some lenses are simply unique. Photographers ask me if they should go full frame, and usually my answer is no. You don't usually need to go full frame until you get to the point where you're lusting over a lens like this, something that you cannot get the equivalent for these smaller sensor cameras. Now, manufacturers are beginning to address this. Fuji has APS-C cameras, and they're starting to release lenses that produce full frame results. This Sigma 18-35 f1.8, while it has a lot of focusing problems, it is designed for APS-C and it's big and fast. There are some solutions, but they're not perfect. They also tend to be kind of outrageously expensive for what you get. Okay, that's all you really need to know about crop factor. That will help you compare different camera systems as you're shopping, if you're deciding whether you should upgrade to a bigger sensor or if something with a smaller sensor will actually get the job done for you. This will allow you to look at the available lenses and determine if they can get the results that you want. There are some misconceptions about crop factor that we should talk about though. One is that especially people who shoot video, say that the smaller sensor of these cameras is actually an advantage. After all, if they're shooting at f2.8, this is giving you the depth of field of an f5.6 lens. That's not really an advantage though, because full frame cameras have the option to shut the aperture down to a smaller f-stop. You don't get more depth of field out of this unless you compare the same f-stop number, which is silly. You should always be converting the f-stop and the focal length anytime you're comparing results with lenses across different sensor sizes. Another supposed advantage of smaller sensors is that the lenses are smaller. For example, here is a 12 to 40 millimeter f2.8 lens designed for small sensored micro four thirds cameras like this. If you apply the crop factor to the focal length, you would find it's about the same as a 24 to 70 on a full frame camera. Here is the 24 to 70 on a full frame camera, and as you can see, the full frame lens is substantially bigger than the micro four thirds lens, even though these are both f2.8. However, this math only works if you forget to apply the crop factor to the aperture when you're doing these comparisons. When you do apply the crop factor to the aperture, you'll find that lenses are about the same size based on the results that they give, not based on their physical measurements. This Sigma 18 to 35 f1.8, it's designed for APS-C cameras and it produces about the same results as this lens. And if you look at them, you'll see that they're also about the same size. We see this time and time again. Of course, there are some variations. There are full frame equivalent lenses that are actually smaller than the equivalent micro four thirds and vice versa. But overall, the results that you get determine the size of the lens that you need to use, and there ain't no such thing as a free lunch. Smaller sensor cameras can be smaller in one way, in that the lens mount itself can be quite a bit smaller. That means that lenses can be designed smaller at the low end, like this tiny little lens that fits on here and is smaller than any full frame lens that I've ever seen. If you're interested in very small lenses and you don't have any interest in low light gathering capability or lots of background blur with those lenses, then smaller sensor formats might be the right choice for you. You'll definitely get people, especially lens manufacturers, telling you to apply the crop factor to the focal length, but not the aperture. They often do this because it overstates the power of their lenses. That's pretty convenient, especially if you're trying to sell somebody lenses, right? For example, this is the 300 millimeter f4 from Olympus. It's a micro four thirds camera, so the focal length in equivalent terms would be 600 millimeters. Olympus often likes to compare it to the 600 millimeter f4 lenses from full frame manufacturers, and as you can see, this would be great. As a wildlife photographer, I would love to carry this instead of this. But the fact of the matter is, as like I said, there's no such thing as a free lunch, and this big lens produces much better results than this little lens. Trust me, I wish that we could do this math. I wish smaller sensors just made every lens more powerful, but that's just not the case. If that were the case, then we would all be taking our smartphones with their tiny little sensors and putting them on these things and just having like infinite amounts of power. I could take this smartphone and put it on this $100 50 millimeter f1.8 lens, and if I did this, it would be more powerful than that big 600 millimeter lens. If that math worked, that's what everybody would be doing. We all want that, but that's not the way physics work. There is no substitute for a big, huge front element that is gathering a ton of light. That's what produces all that background blur. That's what gives you amazing low light capabilities. And like I said, once you actually do the crop factor equivalence math, the results you get are pretty much determined by the size of the lens. You just can't cheat that. If you're a little nerdy, I can actually give you some additional proof. There's a formula for f-stop. The way it's calculated, it is the focal length of the lens divided by the opening, the iris of the lens. Therefore, if you are saying that this 300 millimeter f4 lens is actually a 600 millimeter f4 lens, you're applying the crop factor to the focal length in the focal length, but you're not applying the crop factor to the focal length in the aperture formula. And if you took basic algebra, you know you can't apply something to one side of the equation and not to the other. It simply doesn't work out. If you do apply the crop factor to both of them, then all the math works out perfectly, including factoring in the opening of that front element. Is that a lie? Are manufacturers lying to us? I mean, maybe not technically. Here's what it's like. If a car manufacturer told you that their car did 0 to 60 in 2 seconds, but they didn't tell you that they were talking about kilometers per hour instead of miles per hour. Technically, they're giving you an accurate physical f-stop number, but they're not pairing it with the physical focal length. If you want to talk about lenses in equivalent terms, fine. Apply the crop factor to both the focal length and the f-stop. If you want to talk about a lens in physical terms, fine. Don't apply the crop factor to either. But you cannot selectively apply the crop factor to one and not the other without deceiving yourself or somebody else about the power of the lens. Here are some frequently asked questions. What about medium format cameras? Medium format cameras have a crop factor of less than 1. So the Hasselblad medium format camera has a crop factor of 0.69, and otherwise the math works exactly the same. Why do we use 35mm as the base for all this and not APS-C or Micro Four Thirds? Oddly, you have to blame Thomas Edison. This goes back to the late 1800s and early 1900s when the first movie cameras were being developed, and Thomas Edison, on his precursor to the real movie cameras, settled on 35mm film. It became a little bit cheap, and then still camera manufacturers started using that same film format for their cameras. Leica picked it up about 100 years ago, and it has been the most popular format since. We only convert to 35mm because that's what everybody is already familiar with. Another question, does crop factor affect exposure? I covered this at the beginning of the video, but I'll say it again. Crop factor does not impact exposure, not in any way. We covered this in our first crop factor video at about 16 seconds in, but people still bring it up because they're trying to debunk crop factor, this very simple conversion. Your meter doesn't need to tell you anything about crop factor because crop factor does not affect exposure. Crop factor is a conversion that is useful for determining the final image you will get out of a camera and lens pairing. Another argument you'll hear is that it's not the crop factor that matters, but the pixel pitch or the pixel density. And this works out only if you are comparing one pixel on one camera to another pixel on another camera. If your idea of photography is looking at individual pixels, then yeah, crop factor doesn't matter to you. But most of photographers are using the entire sensor and not just one individual pixel to make a picture. Another common question, do full frame cameras gather more light than cameras with smaller sensors? The answer is yes. At any given ISO, at any given f-stop, the full frame camera is gathering more light because, of course, with that lens, there is light hitting the outside edges of the sensor. With a smaller sensor, that light is simply being lost. Using a lens designed for APS-C or Micro Four Thirds does not concentrate the light any more intensely. If you're at the same ISO, it's the same light per square unit area falling on the sensor. Thus, given the same exposure settings, bigger sensors would always receive more total light, and that's why when you do these comparisons without using crop factor, you see that bigger sensors are typically producing less noise, again, if they're of the same generation. There is one cool hack to work around this for smaller sensors, especially mirrorless cameras, and it's speed boosters like this one, and we use them every single day. Speed boosters work the opposite of a teleconverter. They take the light coming from a lens designed for a bigger sensor and focus it down for a smaller sensor. That way they're actually magnifying the light. This particular speed booster is 0.64 times. So if I were to put a 100mm lens on it, it would start acting like a 64mm lens. And just like crop factor, you would apply that speed boost multiplier to both the focal length and the f-stop. So an f2 lens would suddenly become an f1.3 lens. It allows us to produce genuinely full frame results with smaller sensors. We use it in our studio all the time because the cameras we have there have small sensors. And I would like to make that point. Understanding this math allows us to use cameras with smaller sensors. It doesn't make us full frame snobs. We still often use full frame cameras like I am now when we need those specific results. But whenever we can, there are a lot of great cameras that have smaller sensors, and getting the most out of them just requires doing a little multiplication.